try to talk about the non-local means for the denoising, and for the second one, just try to figure out the super-resolution reconstruction. And because I think my presentation is so long, just for today, I just mentioned about the non-local means for denoising, and for the next, this week for the next. But for my next presentation, I just talk about this resolution via non-local means. Today I just want to talk about the image self-similarity, and after that, talk about the non-local means method. Then I will talk about the weights of the NLM, and try to solve the penalty function for the NLM, and I will show you some results for the denoising via NLM. And for the next, for my next presentation, I just talk about the rest of that for the super resolution. For the start, try to figure out what's the image self-similarity in mathematics and in the real world. We have the property that we call it self-similarity, and it means that a self-similar object is exactly similar to part of itself, and it means that that object wants to or desires to repeat itself in some part of itself. For example, for the real world, coastline is one of the self-similar objects. Recently, Hollis and Cole tried to apply this property on image denoising, and that they try to apply this idea for the image denoising, and they call it non-local means method. NLM filters based on the assumption that the image wants to repeat itself with some neighborhood. It means that each image for the each pixel and its neighborhood wants to repeat that neighborhood with that pixel. Wants to repeat itself with the other pixel in that neighborhood. Although the NLM is the weakest among the recent motion estimation video denoising algorithm, but because it's so simple, a lot of people just want to work on that. For the denoising via the NLM, it means that the denoising obtained by replacing every pixel with the weighted average of its neighborhood. And the weights for its computation are evaluated by using black matching between image patches that center around the center pixel to be filtered. And I think in this slide, we can show you how you can use the non-local mean for the denoising. It means that the denoising each pixel is done by averaging all pixels in its neighborhood. And what's the meaning of the averaging? The averaging means that each of the pixels in the relevant neighborhood is assigned a weight. That this weight reflects the probability, and that probability shows that this pixel and the pixel to be denoised had the same value prior to the additive noise degradation. The formula for the NLM is this. You can see here, this formula is for the NLM, and just assume that the X is the output result, Y is the input result, and the noisy image.
Why do they call it non-local? I I think it's pretty local, like you have neighborhood.
This one is for local, but for the exactly for the denoising, for the using the NLM, they just try to not for the neighborhood. They want to for the each pixel. They want the weight for the whole image. For,
So
yeah.
you're describing here is not NLM. Like the formula you're showing here.
Yes, but yeah, I think maybe I think it's true. The topic is not the topic is not true because it's mean that we just this one is this we can call it changed NLM, something like that. Just a specific the whole image to the just the neighborhood.
How do you get W?
Yeah, I can show you. Just first, I can just figure out this one. The X is it's the output result, Y is the input result, and the K and L is mean that for each pixel in the output result, we should find this formula for that. And RJ is in the neighborhood of the KL. And the WKLRJ is the weight for the RJ is the neighbor pixel. And okay. For the weight for the NLM, that the weight of the KLRJ just find in this formula. R hat KL is mean that the operator that extract the patch from an image is mean that the RKLY the patch of the patch in the image Y that's centered by K and L, and respectively for the RJ you can say something like that. And what is F? F is the function for the as a geometric distance and is the non-increasing function. It means that we're trying to have the weight for the each KL that the pixels that are far away from the KL as the weight for the KL. But then if we want to have the weight for KL, that all of the RJ in the neighborhood has the weight on the KL.
So what is function F?
Yeah, the F can be Gaussian function or the box function or a constant.
What's the effect of F on weight?
Yeah, exactly. I said that, for example, here. It's the KL, and this one is the neighborhood of the KL. Want to find the weight for the each RJ in this neighborhood, and if we use F, and this means that for example, if IJ here, because this IJ is far away of the KL, the first function maybe should be is small. But we use the F, the function F, that shows that this distance just have just increase this weight of the IJ on KL.
You mean you want to increase the effect of the far neighbors?
Yeah, exactly. Yeah, I want to just increase the effect of the far pixel on KL.
increase or decrease?
No, increase the effect of the far pixel on KL.
So you said it's a Gaussian function.
Yeah.
Gaussian function represents okay.
Yeah, the non-increasing is just for the nearest pixels here.
So you're talking about f, right?
Yeah.
So here, the more the further the distance, the more weight you put on it. So because here is the distance between the
Yeah, K and I. If Ij should be there, just find the distance this distance.
But if the distance is longer,
Yeah.
do you want to put more weight or less weight?
Yeah, because the first term for this area for this Ij has the less.
Yeah.
Yeah. Because of that, we want to just
Compensate.
increase that one.
Okay.
But no, the first term has nothing to do with it. The first term you need to see, look at if like the two patches are similar or not, right?
Yeah, but
There's no distance information there.
yeah, but for the image, maybe we can just assume that the near pixels, yeah, in the near to the KL has the more similarity to the KL.
Yeah.
Yeah, and for example, this one, if you have the 1 pixel here, 1 pixel here, this one should be so close or similar to the KL. But we want to have the also this Ij. Yeah, we need that the weight of this Ij on the KL too.
Do you implement this? Do you have the code or like do you implement this?
Yeah,
So your what do you use for f? Like you use
yeah, I just
Gaussian
put the
function?
constant.
So you're not using anything, right? You're not using f, right?
Yeah, we just ask the author of this paper. They just say that we can use anything of that one, and we can use as a constant.
But then if you're using a constant, you didn't say like whether it should be bigger or smaller or whatever, right?
Yeah, but no. But the f, if f is a constant, yeah, it just yeah, it should be.
So you use this value, x
Yeah.
equals to y.
No, that doesn't mean a constant.
Right,
That's
but here it's like
it's not a constant. It's just
No, it's not a constant. But if it was a no, I mean that it was. I mean that as a constant that the
okay.
f
Okay, it's
KL
not a
is-
constant. Yeah.
Yeah, it is.
So do you try other possibility? Let's say the Gaussian function.
Oh no, I just use this one.
Okay. That's so weird.
For example, the distance of the, for example, point of Ij and KL is, for example, long. The first part must be small because the image change fast, and the first part start decreasing, and with the f function it can improve the value that the image
Well, I
does.
think it has nothing to do with the first term because the first term is just like comparing if two patches are similar or not, right?
Yeah, but the far away, yeah, the
It
far
doesn't.
image.
I mean, the second term is using the so it really has a. I guess if it's like a Gaussian, it makes more sense if you think of like stuff far away, it's less likely to be useful or meaningful. Then I would first guess like pick a f as a Gaussian function instead. But you said that it can be a geometric distance, then that's basically what you are using, right?
Yeah.
What you're using is geometric distance, not a constant. And a box function would be similar to a Gaussian also, like bigger than
Maybe because of the constant is so simple, they use the geometric distance for that.
Yeah, I guess I should look at the paper. Like, I want to take a look of all the things, like that particular sentence.
Yeah.
You can have it here.
Yeah. This is exactly so this one.
Yeah, I guess it's talking exactly the opposite.
That's a not increasing.
This moment, not increasing,
Yeah.
right?
Not
So
increasing
this
for
guy is supposed to be like increasing.
no, but not increasing for the point the nearest pixels for the K and L.
No, it doesn't mean that. Actually, it means actually decreasing. Here, it's same like it's many form, right? Gaussian box function or constant. Constant also like basically not changing, so it's not increasing or decreasing. You're exactly doing the opposite, not increasing.
But for Gaussian doesn't mean
Gaussian is a Gaussian bell shape.
Yeah, I mean that they said that the function f for the Gaussian and the box function. For the box function and the Gaussian is exactly
Yes,
yeah.
it's not decreasing, right? So it's not non-increasing, it's basically it's decreasing. So that is definitely not right. Like all the implement is not what they intended. I guess maybe you should try to also like but you'll leave it later, I guess.
In this slide, I will try to in an area energy minimization, and just try to define the penalty function as here. We have two desires for that. The first of all, we want to have desired proximity between the reconstructed and the input images. It's the classic electrical term. And in the second term, we want to have each pixel, each patch in the resulting image to be locked to other patches in the neighborhood. So we define this penalty function. For the minimizing this penalty function, just get the direction of the direction of this.
So this is saying after noising.
Yeah, the x is the output, y is the input. This one is the noisy image, this one is the reconstructed image.
And this term is saying for after construction, each patch should be similar.
Yeah, exactly. Exactly. Isn't that the after?
That's similar. Not exactly, but similar.
Yeah, it was similar. Yeah, this one is the second term is exactly something that we said before. Yeah, here. We want to have for each patch, we want to have similar patches in its neighborhood.
So what's omega?
Omega is mean the whole of the pixel, whole of the pixels of the Y.
Okay. So what do you use for neighborhood?
What do you use?
The neighborhood, like MKL.
Yeah, I said before that the N is the neighborhood and the KL is the each pixel of the Y and X K is each pixel of the X and RJ is the
So
pixel
how
of the
big is the
neighborhood.
neighborhood? Describe the
Yeah, because for the neighborhood, they call it search area.
Uh-huh. So
And just, for example, before the running the code, just assume that the neighborhood is, for example, this size.
how big is that?
For example, for Foreman, it's almost 31st to 31st. 31 and 31, yeah. But for example, text, they use the another search area, yeah. Okay, here just write up that plant function as that equal to 0, and just open up all of the brackets, and we have these functions, these terms, and here we have some assumptions. We just for the call it the neighborhood as a symmetry. It means that if ij, if ij is in the neighborhood of the KL, then the KL is the neighborhood of the ij. It's so easy, and you can see that, for example, for this area, or maybe just it's KL, and this one is the neighborhood of the KL. If we exactly assume the neighborhood of the IJ, so if IJ is in the neighborhood of the KL, then KL is in the neighborhood of the IJ. Exactly, you can see that. And for the second assumption, the weight is also symmetric. So that the weight KL ij is equal to weight ij KL. And for example, here you can see that. Yeah. Okay. With this assumption, we can just say that this equation, this term is equal to this term for we can just choose that the ij to KL here, and also for this two. So for this assumption, we can have that this term equal to this terms, and this term is equal to this term. So after applying that assumption, we have this equation, and now we try to solve this equation for the image. We use an iterative approach for solving that equation, and for that, before that, just define that x n-1 as an outcome of the previous iteration, and xn as a desired outcome of the current iteration. So just put the xn, and x minus n here, and try to solve this equation. But before that, for the simplicity of this one, we call it this summation of the WKLIJ for the all of the IJ in the neighborhood of KL as a W bar of the KL. So we have these equation after putting the xn and x minus n, and for the initialization of the x0 as a y, this means that for the first image, for the outcome image, we put that one, we put a noisy image for the result image, desired image, and then try to use that iterative image to solve it. So for the finding the x hat, we have this equation after put the x0 to y, and the desired x would be x1. For the simplicity of this equation, because instead of extracting the patch of each pixel in the neighborhood, we just have the Rij as extracted just one single pixel in that location of the Rj. So this equation just refer to this equation, and
R is 1 pixel.
yeah. For the simplicity, we just simplifying this equation, just assume that the Rij equal to this Rij equal to just 1 pixel, not the patch.
The RKL is still a vector.
Yeah, RKL is the patch. So we have this equation after this assumption. Now for finding the x hat,
So for this is the scalar value.
yeah,
This is the scalar.
yeah,
This is the vector.
yes.
And this is the identity matrix.
And I is the vector.
Can you go back? I was. So you said which one is scalar again, and what was the assumption?
This one is the scalar. Yeah, because we assume here this one.
Okay, this is scalar, yeah. But
Yeah.
you say Rij something like.
Yeah, Rij is just as a 1 pixel.
Can you go back a lot? Like, let's see. Oh yeah, maybe here is good place. But if you change Rij to 1 pixel, you need to change RKL also, right? Otherwise, how to compute this distance? I mean, you want to compute the difference of.
Yeah, both of them are the 1 pixel.
So you need to change RKL to 1 pixel.
Yeah, exactly. But first of all, just to assume that the Rij is this one, is just for 1 pixel, okay? And we have the RKL. RKL is exactly 1 pixel again. But if we change this one as a 1 pixel, it means that we want to find the XKL, and just RK is equal to just 1 pixel.
So the R transpose KL. So if RKL is a scalar or
And RK is just 1 pixel.
so it should be RGB or it's a value, single value.
No, it's just, no, it's the, yeah, single body.
Actually, can you go back those slides again? Maybe more. Oh, okay. So so next slide.
Next slide.
So this is the one after you take the derivative, or
Yeah.
so maybe go back to the one you're taking derivative.
Yeah. Yeah.
Yeah, next one.
Yeah. So no question?
What's the dimension of the identity matrix?
Which one?
The matrix, identity matrix, lambda times I. Because I thought if they are all scalar, this term should be scalar. This whole term, but this is a matrix. I don't know how to add.
Yeah. Not. For the here RKL, just RRJ is just one single, yeah, just it's a single pixel, okay. If we just use the RKL, RKL for the each pixel is just one, yeah, just a single. But for the first, yeah, equation, we use the RKL, not just one single, because we just trying to figure out the x. Okay, but if you just think about each pixel here, I mean the XKL, RKL should be just one pixel. And I is just equal to 1. Mean that the first term, just find all of them, all KL, and what we just say that the XKL here is mean that it's just one point of that big matrix.
Excuse me, one question. This term, for example, this one equal to 1, 1, and 1.
Yeah.
You bring here.
Yeah. Yeah. This term is just for all of the image, but here we just here we just find each pixel in the X. So for this one, RKL is equal to 1. It means that they just extracted just single pixel, and I is equal to 1. So it has the lambda. This one is the W, and we got just because we just define the W for here, W, K, or Ij, and most of them is the 1. And for here, exactly we have this equation, these steps here.
Yeah, okay. I guess from the paper it's clear maybe that because it's thick back and forth through multiple slides.
Yeah, if you have any question, you can ask.
Yeah. Maybe if you go back one equation, it's better.
Yeah.
So like she has that formula, right? That the next equation is now here. She just like they assume that our Ij is operator only in one single pixel. So then the next side become Yij there.
Yeah, I think it was my fault because I had a lot of back and forth for the slide, and we just fix it. Yeah, just think about it. This one is just operated for all of the image, and here just we try to just for each pixel of the KL. For each pixel of the KL, we want to find the W for this neighborhood, and after that multiply up to the Yij. The Yij is just 1 pixel.
So then the last equation is that you also assume like our KL is 1 pixel.
Exactly.
Okay.
Yeah. And okay, and another thing is that if the R here, and we have 2 R. One of them is just R, and the 1 R is just reused in the W as a weight. It was R hat, no, that's not R. So we have 2 operator that extract the patch. For the W, okay, let me just.
Is this exactly what they implement?
Yeah.
Eventually in the experiment?
Yeah.
Okay. I mean, it looks pretty good actually.
Yeah, I think it's so simple. It's really simple. Okay, just think about this one. For the weight, we don't have just one single. We have R hat, okay, and R hat for the W. Yeah, here. We have R hat KLY and R hat IJY. It means that for each of them, for defining W, for defining the W of the okay, just go ahead. This should be RJ, and this one is the KL. Okay, and this one is the neighborhood of the KL. Okay, so for defining the W is the summation of all of them. Okay, and just for defining this W of the KL and RJ, we have the R hat of the it should be like that. Okay, and just as a that one as if so for defining the R hat, for example, in that paper for the superresolution, they assume that the R hat has the size of the Q, that Q by Q, and has the, for example, it has the 13 by 13. Okay, and the neighborhood, the size of the neighborhood of the 21 to 31. It means that for each of this one, whether like this patch and this patch always the same. Just find for all of the dispatch and this just put in this formula and find me the W, K, L, R, J. And for the final formula, we have the W as a W bar of the KL equal to the summation of the all of this KL ij. Okay, for the all of the ij in this neighborhood. Okay, so we have two patches, two kinds of patches. One of them is just for the W and finding the weights, and one of them is for the defining the X KL. And for this KL, the patches is equal just for the single pixel. Okay, but for the W, it's not. For the W, we have the patch the size of the cube by cube. Okay, yeah, and we can use the non-single pixel, something for example p by p. But for the to have a simple formula, we use the just single pixel. So after finding this W, for finding the X of the KL, we have something like that. It has the W. Okay. The Yij. Oh no, Yij. It means that we just find this weight, and after that, just multiply this weight to this pixel, okay, and just find the summation of all of them, and after that, just normalize by this weight. Right?
Example.
Yeah. I think the point is that we have two operators for the patches. This one and here. And we just don't mention about this patch, just find the single pixel. And for this one, just we have the cube by cube, the patch of the cube by cube for finding the W. And for we call it non-economic. This one is it's not the change, it was changed, non-economic. But for the denoising, we don't have any neighborhood. Just find for each pixel as a KL, the neighborhood is exactly omega. Exactly is the whole image. It means that for each pixel, just find all of the weights of the pixels by KL. If you change KL to here, exactly you just have this same way. And finding the weight of all of the pixels with this KL, after that finding the XKL. And this one is a general, just change this one for the generalizing for the superresolution, and because of that we just define the neighborhood for the KL. Yeah. So we have just one result for that. And for example, this one is a noisy input image, and this one is a denoised image. And if you want, I can show you in the website. Maybe I can. They have nice online demo. For example, you can just for example this region and just this one is a noisy image, this one is a denoise image, this one is the original image. And so they just find the difference of the both of them. And maybe we can just find the small patch of that. For example, this was a noisy image, it was the noisy. Okay, maybe this one is not good. Let me show you. Yeah, you can. I think this one is like whenever you can just see in your computer with each image. Yeah, I like this demo. It's very good.
Oh, okay.
Yeah, I have the second part for super resolution, but I think
Oh, okay, maybe
yeah,
next
it's-
time, yeah.
Yeah, we have a lot of